Our universe is a vast and mysterious place, filled with wonders that boggle the mind and stretch the limits of our understanding. It's filled with billions of galaxies, each containing billions of stars, planets, and other celestial bodies. But have you ever wondered where it all came from? How did this magnificent universe come into existence? How did this incredible cosmic tapestry come to be? What event sparked the birth of everything we see around us? The answer, scientists believe, lies in an event called the Big Bang, a moment of creation that set everything in motion. Imagine the universe concentrated into a tiny point, smaller than an atom, a singularity of infinite density and temperature. Then imagine this point exploding with unimaginable force, creating space and time itself, and giving birth to the cosmos. This is the essence of the Big Bang Theory, a cornerstone of modern cosmology. This wasn't an explosion in the traditional sense, like a bomb going off, but rather an expansion of space itself. Instead, it was an expansion of space itself, stretching in all directions at an incredible speed, carrying galaxies with it. This theory, developed over decades of scientific observation and study, is the best explanation we have for the origin of our universe, supported by extensive research. It tells the story of how our universe evolved from an extremely hot, dense state to the vast and complex cosmos we observe today, a journey spanning billions of years. The Big Bang Theory isn't just a guess or a wild idea. It's supported by a wealth of evidence, from the afterglow of the Big Bang itself to the distribution of galaxies throughout the universe, all pointing to this monumental event. For centuries, people believed in a static, unchanging universe. This view was championed by great thinkers like Aristotle and Ptolemy. They envisioned a universe where Earth was at the center, and the stars and planets moved around it in fixed orbits. However, in the early 20th century, this view began to crumble. Astronomers started to notice things that didn't fit with the static universe model. They observed that galaxies were moving away from us, and the farther away they were, the faster they seemed to be receding. This observation was revolutionary. It suggested that the universe wasn't static at all, but rather it was expanding, like a balloon being inflated. The idea of an expanding universe was initially met with skepticism. Even Albert Einstein, who revolutionized our understanding of gravity with his theory of relativity, was hesitant to accept it. He initially introduced a cosmological constant into his equations to maintain a static universe model. However, the evidence for an expanding universe continued to mount. In 1929, astronomer Edwin Hubble made a groundbreaking discovery. By studying the light from distant galaxies, he found that they were indeed moving away from us. Moreover, he discovered a relationship between a galaxy's distance and its speed. The farther away a galaxy was, the faster it was receding. This relationship, now known as Hubble's law, provided the first concrete evidence that the universe was expanding. It was like finding a cosmic speedometer, allowing us to measure the universe's expansion rate. The discovery of the expanding universe led to a profound realization. If we rewind the clock far enough, all the matter and energy in the universe must have been concentrated into an incredibly small, hot, and dense state. This was the genesis of the Big Bang Theory. The term Big Bang was actually coined by Fred Hoyle, a staunch critic of the theory. He intended it to be sarcastic, but the name stuck, and it has captured the public's imagination ever since. The Big Bang Theory postulates that the universe began around 13.8 billion years ago from this extremely hot and dense state. In the first fraction of a second, the universe underwent an exponential expansion, increasing in size by an unimaginable factor. Section 5. The First Moments. A universe of pure energy. In the first fleeting moments after the Big Bang, the universe was a seething cauldron of energy. Temperatures were so high that matter as we know it couldn't exist. Instead, the universe was filled with a primordial soup of elementary particles like quarks, leptons, and their antimatter counterparts. As the universe expanded, it cooled. This cooling allowed for the formation of the first protons and neutrons, the building blocks of atomic nuclei. However, the universe was still too hot for atoms to form. Electrons, the negatively charged particles that orbit the nucleus, were moving too fast to be captured by protons. This era, known as the radiation era, lasted for about 380,000 years. During this time, light couldn't travel freely through the universe. It was constantly being scattered by the free electrons, much like light scattering in fog. Section 6. Formation of matter, from energy to atoms. As the universe continued to expand and cool, a crucial transition occurred, the formation of atoms. Around 380,000 years after the Big Bang, the temperature dropped enough for electrons to combine with protons and neutrons, forming the first atoms. This event, known as recombination, had a profound impact on the universe. With the formation of atoms, the universe became transparent to light. Photons, the particles that carry light, were now free to travel through space without constantly being scattered. The light released at this time, known as the cosmic microwave background radiation, is still detectable today. It provides a snapshot of the universe as it was just 380,000 years after the Big Bang, like a baby picture of the cosmos. Section 7. Birth of stars and galaxies, lighting up the cosmos. After recombination, the universe entered a period known as the Dark Ages. Not because it was dark in the traditional sense, but because there were no stars to illuminate it. This era was a vast expanse of emptiness with only the faint glow of cosmic background radiation hinting at the universe's potential. However, this period was far from uneventful. Invisible forces were at play, setting the stage for the next cosmic drama. Gravity began to pull matter together, forming vast clouds of gas and dust. These clouds, known as nebulae, were the cradles of future stars. Within these clouds, denser regions began to collapse under their own gravity. These regions, called protostars, were the seeds of new stellar life. As these regions contracted, they heated up, eventually becoming hot and dense enough to ignite nuclear fusion, the process that powers stars. This ignition marked the birth of a star. The first stars were born, massive and short-lived, blazing with a brilliance never seen before. These stars were the universe's first beacons of light. These early stars played a crucial role in shaping the universe. Their intense radiation and stellar winds began to carve out the cosmic structures we observe today. They produced heavy elements like carbon, oxygen, and iron, seeding the cosmos with the ingredients necessary for life. These elements were forged in the hearts of stars through nuclear fusion. As these stars exploded as supernovae, they scattered these elements far and wide, enriching the interstellar medium. This cosmic enrichment paved the way for the formation of planets and eventually, life itself. Section 8. The expanding universe today, a never-ending story. The expansion of the universe didn't stop after the formation of stars and galaxies. In fact, astronomers have discovered that the universe's expansion is accelerating. This discovery, made in the late 1990s, came as a complete surprise. The driving force behind this accelerated expansion is thought to be a mysterious entity called dark energy. Dark energy is thought to make up about 68% of the universe's total energy density. It's a form of energy that permeates all of space, acting as a sort of anti-gravity, pushing everything apart. The discovery of dark energy has profound implications for our understanding of the universe. It suggests that the universe's ultimate fate is a continued expansion, becoming increasingly cold and diffuse over time. Section 9. The future of the universe. What lies ahead? The future of the universe is uncertain, but the Big Bang theory, combined with our understanding of dark energy, provides some clues. This theory, which describes the universe's birth and its subsequent expansion, is a cornerstone of modern cosmology. If dark energy continues to dominate the universe's expansion, as current observations suggest, then the universe will continue to expand forever. This relentless expansion will have profound implications for the cosmos. As the universe expands, galaxies will be pushed farther and farther apart. The vast distances between them will grow even more immense, making intergalactic travel an even more daunting challenge. Eventually, the Milky Way will be so isolated that our cosmic neighborhood will consist of just a few nearby galaxies. This isolation will change the way we perceive our place in the universe. The night sky, once ablaze with the light of distant stars, will become increasingly dark. The stars that we see today will slowly fade away, leaving a much dimmer sky for future generations. However, even in this ever-expanding universe, new stars will continue to form in the Milky Way and other galaxies, at least for billions of years to come. This ongoing process of star formation will ensure that the universe remains a dynamic and ever-changing place. Our own sun, for example, is about halfway through its lifespan. It will continue to shine for another 5 billion years before it exhausts its nuclear fuel and transforms into a red giant. The Big Bang Theory doesn't answer every question about the universe. There are still many mysteries that remain unsolved, such as the nature of dark matter and dark energy. It doesn't tell us what existed before the Big Bang, if anything, or what the ultimate fate of the universe will be. These questions continue to intrigue scientists and fuel ongoing research. However, it provides the best framework we have for understanding the universe's origin, evolution, and future. This framework helps us piece together the story of the cosmos from its fiery beginnings to its expansive present. The Big Bang Theory is a testament to the power of human curiosity and our quest to understand the cosmos. It showcases our ability to unravel the mysteries of the universe through observation and scientific inquiry. It reminds us that we are part of something much larger than ourselves, a universe with a rich history and an even more awe-inspiring future. As we continue to explore and learn, we deepen our connection to the cosmos and our place within it.